Hello and welcome to the video. And until now, we saw what all kind of not noises we can have in our circuit, and we also modeled them. So now in this video, we will see how noise can be scaled in a circuit. So let's come to noise scaling, and let's take a simple example which we took earlier of a simple common source amplifier. So let's take a common source amplifier, and let's assume that it's biased already, and we have a noise source in series with our large signal. And now let's do one thing. So for the sort of example, let's do one thing that we let's take the exact uh, replica of this circuit and connect all of the nodes exactly. For example, the gate will be connected to the gate, and the drain will be connected to the drain. All the values of the components are exact same, and M1 has its n equals to width by length ratio, and M2 has the same width by length ratio. So over here, we can say that no matter how complicated two circuits are, if they are identical and we connect the corresponding nodes to each other, so we will have a same functionality as we had earlier with the single circuit. So what does this actually mean is this structure will have the gain of minus GM times R only, and it is the same gain we had when we had our simple structure. Now the complete structure will also have the gain of minus gm times r, but what changes is actually we can say that this structure is equivalent basically to this structure over where our r, so basically r, this r which is in parallel, reduces to r by 2, and its noise can be represented like this. And basically what changes is the ratio of width by length of the MOSFET, which gets doubled in this case. So the noise has changed multiple, like here we can say that our SI has changed to twice in case of resistor, because now what we have is the SI due to, or the noise due to the resistor is 4 kT divided by the total resistance, and earlier we had 4 kT divided by R, and now we have 4 kT divided by R by 2. So the total value of SI is twice as earlier. And similarly, the noise from MOSFET, the current in MOSFET has doubled, and we have same VGS. So width is doubled, and this will double the GM as well. So the noise in NMOS is basically 8 by 3 kT times 2 GM because of the width. And so originally what we had was, originally we had simply this one single structure, and which was represented by this. And originally we had our total output noise density as 4 KTR plus 8 by 3 KT GMR square. So this was our output voltage noise spectral density. But now after implementing this circuit, what we have is basically this kind of a structure where our R is R by 2, and now due to this noise, we have basically 8 kTR by R by 2 square when it comes to converting SVN from SIN, and basically SIN is this. So we will multiply it by the square of resistor value. We have done this equation earlier as well. So the value comes out to be 2 kTr. And similarly for the MOSFET, the value comes out to be 4 by 3 kT GMR square. And when we look at carefully, look at it, so the output voltage noise spectral density will be basically the sum of it, or basically this value divided by 2. So what, like, where like SVN is basically from the original case we had. So basically what we are saying over here is when we had our original case, we had some noise spectral density, and now when we implement this example of identical circuit and connecting the corresponding nodes, what we are getting is the SVN is reduced by half of its value. So we can say that when we go from the original case, with omega by L as its ratio and resistance R, to the actual case where we implemented 2 omega by, sorry, 2 width by length, and the resistance became R by 2. So SVN becomes half or reduces by 2. So thus two identical circuits of which corresponding points are interconnected. Then the noise current sources will appear in parallel, and so basically the noise current sources of these two circuits will appear in parallel. And what we are saying basically here is the spectral densities will double actually for over here. For the current spectral densities, they are actually double, but due to the resistance becoming half, the spectral density of the output, so the main output voltage over here, so the spectral density of output voltage, due to the R becoming half, the result is the density will reduce to half. And also, if we take some two identical circuits, but the other circuit is scaled by the factor of n. So now here the other circuit is scaled by the factor of 1, because we have all the component values scaled by 1. Now if these values were scaled by some other factor, let's say the factor of n, then the output spectral density will scale down by the factor of n. So basically, here the scaling, so the scaling was twice. So we had two identical structures. So the output density was scaled down by 2, and now we are saying that if it was scaled by n, so the output spectral density would have been scaled down by the factor of n. So basically this is called as noise scaling, and we can also call it impedance scaling, where we can imagine that we have our circuit and we have our elements in our circuit, and we are providing the power source, or the voltage source, and it is driving a current of I. And now we are saying that we are having over here the I supply, and we are taking the spectral density of output voltage. So now this, like, we can scale it by saying that we have scaled all the elements. So basically what scaling means is the resistance will become R by N, the width of the MOSFET will become N times width, the capacitance will become N times capacitance, and the inductor will oppositely become inductance by N. So what we will get as a spectral density of output voltage is scaled down by the factor of n. This is what we said. So scaling with factor n is basically meaning that our output voltage spectral density will scale down by n, but at the same time it will drive a current of n times I supply. So basically power will will be, or power dissipated will be n times now in our case, like in the case of scaling, and last signal voltages will be identical in both cases. So basically large signal voltage is biasing voltage or something like that. So sometimes our circuit dissipates more than given limiting power. So while we are scaling, or even we are not, when we are not scaling, sometimes what happens is our circuit has the limit of power dissipation, but it is dissipating more power than the limit, or it is crossing the limit. So we scale it down by scaling up all the impedances, but the noise is also scaled up. So basically we are talking about the vice versa thing. So we are talking about the opposite thing. So basically what we said, that now we have a circuit which is dissipating more power than its limit. So what we say is we go the go the reverse way down, and we can scale up all the circuits, and like we can scale up the impedances, but the noise will also be scaled up. So we have the trade-off according to the requirement. So basically we know that our thermal noise was 4 kT by R in resistor and 8 by 3 kT GM in MOSFET. So in order to reduce this noise, we can think of reducing the temperature as well. because absolute temperature is also the factor which is proportional to the noise. So let's not worry as of now whether the circuit will really work at lower frequency, lower temperature or not, but let's assume that it does. And the question is, how much power will it take to cool down a circuit? So we have a fundamental refrigerator, or not refrigerator, but opposite to that, we have a fundamental concept of Carnot engine. And basically it takes thermal energy and converts it to the mechanical energy. So basically there is a concept where let's say we have higher temperature T2 and we have lower temperature T1, and it operates between two temperatures, and it is used like it uses the uh, power from heat to produce the power in mechanical form, and it goes from higher to lower temperature. So efficiency is given by P mechanical, or the power from mechanical source, divided by P mech plus P heat, and this is what we get as efficiency. So we need the exact opposite model. We need the Carnot refrigerator in order to reduce the temperature when we are talking about reducing the temperature to reduce the thermal noise in our circuit. So which uses sort of PMEC and transfers or pushes heat from from T1 to T2, and formula for the efficiency remains the same in this case as well. And in our case, in our circuit, let's say we put some circuit which dissipates the power of PD inside a refrigerator, and it is at T1 and the outside temperature is at T2. So basically this is a refrigerator where the inside temperature is T1, the outside temperature is T2, and here is our circuit dissipating the power of PD. So basically P heat from this formula is nothing but power dissipated due to the circuit. And for circuit to be steady, like to be at a steady temperature, the amount of heat taken out from this system, or let's say from T by N to T, basically T1 to T2, must be exactly equal to PD times the scaling factor N. So basically we'll see it further. PMAC is externally required power, which we need to find out basically in our case. So our efficiency will be given by T minus T by N divided by T. So which is PMAC divided by PMAC plus power dissipated by the circuit. And what we have to find is the external required power which is needed. So basically PMAC is from this formula, like we can say, from this equation, we can say that PMAC is nothing but N minus 1 times PD. So what we had, like let's say earlier we have a circuit, we have components of our circuits, and it is driving a power of PD or dissipating a power of PD, and the noise of the circuit which consumed power PD is given by this square. And after scaling, let's say we do the scaling, now it consumed a power of N times PD, and the impedance becomes R by N, and the width of the MOSFET can be realized by N times the width. So this is the scaling we discussed earlier. And now coming to the concept we are trying to discuss is, let's put that circuit in a refrigerator. So from the formula we derived just now, we will need a PMAC of N minus 1 times PD from outside to control the refrigerator. So we will push this T by N to T using this power, and we can maintain the temperature of required amount for our circuit. And let's say now here a circuit requires a power of PD only, and but we have like reduced the temperature. So after reducing the temperature, we can achieve, we can say that we have achieved of scaling down the thermal noise. So basically the total, like hence the reduce, like to reduce, we can say that the total power consumed is PD plus P mech. So this is PD and outside P mech, and we know P mech is nothing but N minus 1 times PD. And from here we know that for a circuit to be at a steady temperature, the amount of heat taken out of the system from T by N to T must be exactly equal to PD times N. That's what we implemented over here. And from this, the total power consumed is again N times PD, and this does not violates the law of energy, and thus while scaling we required a power n times PD, but we had noise as well. And at this point the noise is reduced as temperature is reduced, and at the same time it is driving the same amount of power. So this is something theoretically we can prove, and hence to reduce the noise by a factor of n, we need more power by the factor of n. So basically, anyway, like if we are doing scaling or we are putting it in a refrigerator, like we can use any method, but to reduce the noise, we will need more power, which is a factor of n. So now coming to the frequency scaling. So let's take a RC circuit, basic simple RC circuit, and we have its noise variance as kT by C, and this we have derived earlier as well. So now let's think of reducing the bandwidth of this circuit. So we can reduce the bandwidth by the factor of n. So basically there are two options. So what we can do is we can scale the capacitor by n, and it will give us the spectral density or the variance of noise by kt divided by nc, as the value of c is scale, and this is called constant R scaling. Or the other option is we can scale resistor by like for over here it is nr, by the factor of n, and we will get kt by c as the variance is independent of resistor. So this is called constant C scaling, and we can generalize this by saying that we can scale the bandwidth by the factor of alpha. So let's see how it is done. So we have a transfer function, and when we plot it against the frequency f, so, and we say that our peak comes at 1 megahertz. Now, if we scale the frequency by alpha times f, so if we basically plot the same function against alpha f, so basically our peak will occur at alpha times 1 megahertz. So let's say if alpha is 2, then if the peak of the curve occurs at 1 megahertz, so after bandwidth scaling by alpha, the peak will occur at 2 megahertz, because it's alpha times 1, like alpha times the basic frequency, so it is 2 megahertz. So we can do this either by again having a circuit, and we can scale it to alpha times f by scaling down the capacitor, and this will give us the variance v square by n. As we know, it is independent of r, and this is called the constant R scaling. Or else alternatively we can scale the frequency by alpha by uh, scaling the impedances and keeping the C constant, and this will give us exactly same. Like over here it was dependent on C, so it was alpha times variance, but over here C is not changing, so the noise variance is also not changing, and this is called constant C scaling. So both circuits or the both alternatives will give us the same scaling, but the difference will be the noise. So over here noise will also scaled, and over here noise is not being scaled. So like in both cases, let's summarize the noise scaling. So it is also known as impedance scaling, because impedance at all the branches changes to the scaling factor. And in here, we scale all the elements of the circuit by n factor without changing the transfer function. And our like conductance changes to n times conductance, or resistance to R by n. And our GM of MOSFET turns to n times GM, resulting in n times width. And we have capacitor as NC scaling, and inductor as L by N, or inductance by N. In this case, our output spectral density of voltage becomes downscaled by the factor of n, but the current derived is n times I, and thus the power is n times PD. And when we come to our bandwidth scaling, what we saw just now, so basically we preserve the transfer function here as well, and but what we require is it should get scaled from the transfer function of h of f to h of f by alpha. So basically we have constant C scaling where the GM is alpha times GM and R is R by alpha, and the variance is constant because it's basically not dependent on the impedances. And we also have constant conductance scaling where C gets scaled and the conductance is constant, so the noise variance also gets scaled. So this is all about the scaling for noise, and that's all for this video. Thank you.